do. I'm going to test what I'm doing here while you do your business, if that's all right, Rach.
Okay, no worries. I just didn't want to do anything that would ruin me to do.
Oh, cheers. Thanks for that. Yeah. What to do? Just close that gap in the curtains.
It's fine with that one.
That's right, I'll do it. Don't worry. Shift these chairs as well. Tried it on the site for the cosmologist tour.
Yeah.
As soon as I started, people came in, just sat right in front.
Yeah. Do that.
Classic.
Okay, do you want to start playing? Do you use a radio mic, Rachel? Not typically. We don't tend to have audiences big enough.
Yeah.
But I can if you need to test stuff.
Maybe just to test that I'm getting the microphone and so I can test the lapel mic and test what the ambient sound is like as well. So, but I don't want to put pressure on you to
No,
do something.
I don't mind. I mean, there's a talk and you need to test equipment. Do feel free to use me as your guinea pig.
Well, you're asking for trouble. mic control itself to get us talking. But the idea is just to get us bored. Yeah.
Rather than one voice in the crowd.
That's it, really.
I like it.
That's all it is. Yeah, that's it. That's all it is. And what I'm doing as well, the whole point is, it goes to YouTube.
So you can do it from here,
Yeah,
straight live.
yeah. The series delay to it.
Yeah. Sorry, turn on the lights when I'm looking in. That's funny.
Why that's so far behind that? Yeah, so that's the two microphones I've got. One up there near the wind thing. Put one down there. You should get general sound, and that one's the radio mics. But obviously, I'm not using one. I have to rethink.
Well, I can use them for now.
Fancy trying it?
Yeah, I don't use them specifically for Taz videos just because we don't live stream them and we don't have enough people using the mic.
Yeah, no one's viewing this. This is just a test.
Yeah.
So don't be.
No, that's fine. I'm happy to test.
Yeah, cool.
Cool.
Record it before then.
So what I will do is I'll just open the doors and let's start letting people in if that's okay.
Yeah.
And then while people come in, I'll just get the mic on.
I'll get a mic out for you.
Thank you. That's if we have an audience because there's currently no one outside.
Could be a quiet one.
Yeah, probably. Although
One,
a
two,
lot of
one,
people
two, three,
went
four.
into black holes. So
Hello. Yeah. What's black? What do you mean black holes? One, two, three, four, etc. Still quite a level on there. I can't boost that. Let's go just. Two, three, four. 5, 6, 7, 8, etc. So just. Choosing 5, 6, 7, 8, 9, 10. It's really good. 1, 2, 3, 4, 5, 6, 7. It's on off, yeah. Switch on the top. Double careful.
and whatever it is you're using.
Yeah, it's all quite quiet, but I can't adjust that. I'll record these and test them. I'll do the same next week.
Yeah.
Get it.
I will be speaking loud and up there as well again when I'm here.
Don't let it put you off, just talk normally.
I do that really well. I do have to talk louder in general.
Yeah. Okay, no worries. I'll do what I'm doing. Just ignore me if possible, please.
Ignore the person behind the curtain, figuratively. Like it's something I think for.
Okay, good. Do you want to sit in near the front?
Don't mind. You're comfortable now, you might as well stay there. So, welcome to the Telescope Talk. My name is Rachel. I'm one of the explainers here, so it's my job to explain things, and specifically in the talk, it will be more about the telescopes themselves. So I do like to give a little bit of the history of the telescopes because having us in the middle of Cheshire, in the middle of nowhere, is a little bit odd, but there is a reason for that. And then also what the telescopes do, so what it's done in its past, a few things might surprise you, and what it does today as well. So, in order to start a story, we need to go way back to the beginning, and that is actually an 80-year journey. So we need to go all the way back to 1945 to actually start our tale. So, back in 1945, the site now would have looked completely different. So there were no telescopes back then. It was quite literally a field and a hut. And this is an actual picture of the very first radio experiment that took place out here in December of 1945. So at the time, the land was owned by the University of Manchester, but not specifically to do radio experiments. It was actually owned so the botany department had somewhere to grow their experimental crops. So there were experiments going on, they just weren't the radio kind. But that was quite useful for one person, specifically, in Manchester, who was a physicist in the physics department, that being Bernard Lovell. So Bernard had an idea to study cosmic rays as part of his research, that was what he was doing, but he had an idea and he designed an experiment that would hopefully allow him to do that. Now, in order for him to do that, he needed to use this bit of equipment that you see in this picture. Now, this is a radar truck, so it is using radio waves, but it is ever so slightly different to how our telescopes operate. So our telescopes, they are radio telescopes. They are collecting radio light from space, but radar, you actually have to send out the radio pulse yourself first, and then it will bounce off something that you've pointed at, and it will bounce back at you, and you've got to pick it up as well. So you've got to send and receive the radar, whereas our telescopes can do that, but they tend to just receive radio coming from space. But the idea behind this experiment was that Bernard would use this piece of kit that he borrowed, and I air quote borrow because I don't think he ever gave it back. The Ministry of Supply gave it to him because World War II had ended and they didn't need them anymore, so he repurposed it for a science experiment. And the aim of his experiment was to find cosmic rays, or at least to find the big electron showers that happen in the upper atmosphere because of cosmic rays. They're a lot easier to find than just one very fast particle coming from space. So electron showers is what he was looking for in the upper atmosphere. So he wanted to send out a radio pulse, bounce it off this electron shower, and he would get that receiver back, that signal back. That was the premise. First of all, he did try this experiment in his lab in Manchester, but because of the surrounding noise from all of the trams and the city in general, there was just a bit too much radio noise, so he couldn't really get any conclusive results. So he had to come somewhere quieter, And that's when he started talking to the botany department, asking if he could use their fields that are all the way out in the middle of Cheshire, so there's no radio sources around to interfere with the experiment, which is perfect. That's exactly what Bernard needed. So he got 2 weeks permission. This is an actual picture of the experiment, and the rest is quite literally history. So from this experiment, with us still being here and a world-leading radio observatory, you would have expected this experiment to be so successful, wouldn't you? It actually failed. It was a little bit of a not great in terms of its intended purpose experiment, but it was still a successful experiment in an unexpected way. Now, it turns out, and Bernard didn't realise this at first because there was too much noise, but now he's not got noise, something else is wrong, and he wasn't sure what it was at first, but then he realised in his maths early on, he actually made a mistake, and he carried that forward. And unlike GCSEs, where you get points for carrying forward, in the real world, it don't work. So if you make a mistake and later on you eventually realise that it's because something doesn't work, which is quite typical in physics, if I'm honest. But that was the case for this experiment as well. It didn't work because he made that maths error, so the frequencies weren't quite right. But that didn't stop it from being a complete waste of an experiment. Because while it didn't manage to detect any of these electron showers from these cosmic rays, it did happen to detect the meteor shower that just happened to be going on at the same time. So Bernard, as a physicist, wasn't actually an astronomer or an astrophysicist. So meteor showers and all of those astronomical events, they're not well known to Bernard. They weren't on his radar, you could say, until they were actually on his radar. And that's what he detected. He detected the Geminid meteor shower. But he didn't plan that because he didn't know it was going on. But when he discovered that it was the meteor shower, after talking to some friends who were astronomers, he realised that actually this is a very good method of detecting meteor showers, because not only does it give you more accurate data about the speed of these meteors, it also gives you more accurate data about the direction of these meteors, and you can do these observations when it's cloudy and even in the daytime, because radio waves can go through clouds, and we're not really needing to worry about the daytime because it's a different type of light, so you don't get affected by light, because previously all experiments when it came to meteor showers had to be done with your eyes, with observations, and this gets rid of all those problems. So it was a really good accidental method of studying meteor showers, and that is kind of why the rest is history. Now, Bernard could have said that actually this isn't really my area of expertise. I really wanted to find those cosmic showers, so I'm just going to read out the experiment and go back to that. He didn't. He carried on with this because it was gaining a little bit of traction in the astronomy world. So he carried on. He got more of these trucks, and over a couple of years, he just never left. So he started to expand from where the original botany grounds were. The university started buying up a little bit more land, so Bernard could continue these experiments. Now, as the experiments grew and as his team grew and various areas of research began, you're going to need a little bit more equipment to enable you to do more research. So it came to 1947, and the team, because he built himself a team at this point, decided to build an even larger receiver because they wanted to see what it would be like to send radio waves to the moon and back, and eventually they also did send them to Venus and back as well. And these experiments, because the distances that you're sending these radio waves are a lot longer, by the time it gets back at you, it's going to be really faint. So the bigger your receiver is, the more likely it is to pick up something that's really, really faint. And that's why they built the Transit Telescope in 1947, so just 2 years, believe it or not. Now, it is also important to mention that this was built by the staff themselves. When they came to site, many of them were, first of all, just physicists, not necessarily astronomers, so they had to learn astronomy as they went. They also had to become engineers because radio astronomy at this point in time doesn't actually exist. They're the pioneers of the field. They made the field. So all of the equipment that they had to use, they had to build. And if they didn't know how to build it, they had to figure that out. And this was one of the really cool things that they did actually manage to build. It is a big dish, essentially, just like all of our telescopes are basically big dishes with a receiver in the middle. That is what's going to collect all of the radio signals. Now, because it's so big, if they turned off the transmitter, they can also use it as just a radio telescope. So they can use it for both purposes, as a radar set receiving those signals that you've already sent out, but also as just a telescope. So when they built the transit telescope, this was sort of the turning point for the observatory into becoming what we know now today to be a world-leading radio observatory. But it wasn't until they built this that it really started to pivot. It was more radar astronomy, and now it's radar and radio astronomy. So there's a slight distinction there. Now, the size of this telescope, it doesn't really look that big in this picture, but it is actually really big. It is approximately 218 foot across, which granted is smaller than Lovell, which is 250 foot across, but it is bigger than our second biggest telescope that we have, which is Mark II, and that's only 125 foot across. So it is somewhere between that telescope behind the curtain and the bigger one over there, so somewhere between those two. And usually when you have such a specific number in physics, there is usually a physical reason for that. But in this case, the reason for it being 218 foot is simply because one of those radar trucks was stuck in the mud and they literally had no other space to build it. So the area between that truck and the edge of the farmer's field that they couldn't build on, 218 foot. So they made it as big as they could, given the space and the truck. So that is why it is a bit of an odd number. But with it, they're able to do quite a lot of physics. Not just use it as a receiver, a really good one, but as I said, as a telescope as well. So with the transit telescope, they got a really good detailed map of Andromeda. And Andromeda is really high in the sky at the winter, so it's actually up quite nicely right now. And essentially, they were the first type of, they were the first team to sort of try and do this. So it was a first. It was really cool. They also managed to rediscover things that were thought to be lost to like history textbooks as well. So one of my favourite stories of using the transit telescope is all to do with this thing called Tycho Brahe's star. Now, if you've heard of Tycho Brahe, if you haven't, that's fine. He was an astronomer a couple of centuries ago. But in his time, he recorded what we now know is a supernova. So this was a very, very, very powerful explosion from a star that died. But that star's explosion was so bright that it was visible on Earth with just your eyes. You didn't need a telescope, you didn't need binoculars, in the daytime, and then for a good 6 months at nighttime afterwards as well. Now over time that faded and the light started to dim. So it was forgotten in history because we're not seeing it every night. But he recorded it, so we have that record of it. And with the transit telescope, they picked up a radio signal from the same area of the sky. Now, again, they're not astronomers, so they didn't know what it was. And there was nothing visual there for them to see, so they weren't sure what it was at first. A little bit of research later, and they find out it matches the records of Tycho Brahe's star that disappeared. And so once they matched that up with the visual and the radio, they got a more powerful optical telescope to see, is there anything there anymore? And there is a very, very, very faint glow in the visual, but it's still very bright in the radio. So it was really cool. They're rediscovering things as well. The only issue they had with the transit telescope was that it was a fixed dish, so it can't look all about the sky, and therefore it's limited in what it can see. So that is where they started to have a few issues later on. They weren't able to see as much as they would like. So they decided to basically build something that would allow them to do that. Now, also, around about the time they were deciding that, Bernard became the world's first professor of radio astronomy, and this picture was taken to commemorate that. So now the things that they're studying is now a recognized field of study. So before it was like, oh, this is cool, but it wasn't an actual field. And now we've got our world's first professor, our very own Bernard Lovell. So this is all of the team outside of one of the other things they built, which is the Searchlight Aerial. They used that again in their meteor studies. But it was about this time where they decided that they needed something that would allow them to see the sky now. So it wasn't just talk anymore, it was serious planning. Now, because the scale of the Lovell telescope is so big, they can't just rely on just this team anymore. They can't make do and mend. They need to get a professional on board to help them with such a big project. So they find an engineer who will help them with the project. And in this picture, we have Charles' husband on the right-hand side, who is said engineer. So Charles and Bernard are the men responsible for helping to plan and then design and then eventually start building the Lovell telescope. Now, the construction on the telescope is started in 1952, but it wouldn't be finished until 1957. Now, there were also a few hiccups along the way, mainly money. How do you fund such a big project? And the answer is taxpayers' money after putting a proposal into the government and they gave the money over. However, the engineering of the telescope, they didn't expect as many complications as popped up. So the budget for the telescope and the project, it quickly ran out. And so they actually ended up spending, by the end of the project, over 4 times their initial budget, which was £120,000. That was how much they were given originally. But by the end of 1947, it was over £700,000 that they spent, and they hadn't even finished it yet. And that was why Bernard got into trouble. So because this is taxpayers' money, and he's not delivered on the promise of a working radio telescope, 2 years over the time, and many monies over the budget, you can see why the British government are just not his friend right now. And it's also understandable about the public not being happy about that. It's their money that has apparently been wasted in their viewpoint. Because again, remember, radio astronomy, very new. There are not many professors in the field. So how do you expect the public to understand why they're building it in the first place? It's understandable. Now, they didn't waste the money. It was more just engineering challenges that were a bit more expensive than they realised. They did actually try to save money wherever possible. And one of the things that they would often do is go to scrap yards to see if they could get as much material that they could salvage and then use that to build the telescope as well. And one of my favourite facts about the telescope is this big circle that you see on the screen. This is a gun turret from a battleship, but it's also the thing that tilts the dish up and down. So one of the scrapyards that they went to was a naval ship scrapyard. Again, taking into account the time period and World War II had ended. So a lot of the ships that had served in the Navy are not necessarily up to regiment standards anymore, so they're being scrapped. But that was very useful for the engineers because they decided that the gun turrets from these scrapped battleships would be the perfect size and shape to tilt the dish. And so it is these gun turrets that still today tilt the dish up and down. So it's an engineering marvel, in my opinion. But also it's made from bits of battleships. And I think that's just a really cool fact. You can see these battleship gun turrets if you look at the telescope as well. So if you look on the towers when you go outside, between the dish and the top of the tower is a big circle that pokes out. It's the battleship gun turret. So have a spot next time you're outside. Now, ultimately, obviously, this was not enough to save them money. And they overran their budget by a lot. The government come knocking to see us misuse the funds. And this is what Bernard is getting into a lot of trouble at this point. However, Bernard had a little bit of luck on his side. So in 1947, when all of this is going on and Bernard is basically almost possibly going to prison over it all, the Soviets launched Sputnik. And Bernard uses this to his advantage to try and pull off the world's greatest publicity stunt to try and get all of the good press his way rather than the bad press. Now, what I mean by that is the whole telescope itself, nobody knows why they're building it in the first place. The public see it as a waste of money. And so if he can convince the public that it's not a waste of money, yeah, expensive, but not a waste of expenses, he could potentially not go to prison, which is good. But it also keeps the telescope open, keeps the observatory open, and his job somewhat secure. So he decided to take a risk, and he uses the Lovell telescope as a radar receiver, going back to his roots, just like they did with the transit telescope. And he decided to do something that was thought to be impossible. With the launch of Sputnik, which is easily found in orbit because it's giving out a beep, you don't want to track that because broadcasting its location, that's too easy. But the rocket that had launched Sputnik is completely silent. That's not broadcasting its location. It's also going really fast, so it's unlikely that you'll see it for a long period of time. And even if you do, it's going so fast it's not going to be in your view for very long. So it's thought to be somewhat impossible to track the rocket. Until Bernard, with his big maneuverable, big radio dish, all of his radar equipment, and also, did I mention that during the war he worked on radar detection systems? So he's also got the know-how to do all of this. So pile all that together, and Bernard actually does the impossible. He manages to track that rocket using the radar kit that he's got here, using the Lovell as that receiver, and he's done something that was thought to be impossible, and that gets good press. It also gets the military very interested in how they could develop this particular type of technology into a potential early missile warning detection system. Now, the reason why that's kind of top priority for the military at the moment is because in the midst of all of this, we're actually in the Cold War. And the Cold War was a period of time where nuclear bombs and the threat of them being flown was very high. So having an early warning detection system that could give you a little bit of time should a bomb come your way, you can see why that's top priority for the military. And Bernard has handed them the seeds of that technology on a silver platter. And so the military come to site, they hire the telescope, so hiring means we get rid of some of the debt. And they use Bernard's expertise, his knowledge, and help develop some of the UK's first early warning missile detection systems with the Lovell telescope as part of that equipment. So, not long after it's in operation, it's built from battleships as well, it's also playing an important part of our national defence, and that's all within the first year of operation. So, that is pretty good. Now, it also means that Bernard doesn't go to prison, he ends up staying and becoming the director, and the observatory stays open. So in all of that time, the early warning missile detection system is only a tiny bit of the stuff they do. They are still now an open observatory doing what they intended to do, which is study the universe for radio waves. We do then also, though, enter a really interesting time period in history, in my opinion, and that is the space race. So it's true, the UK not a part of sending things to the moon and back during this time, but we were a part of the space race in a different way, thanks to the telescopes here at Jodrell Bank. And that's because we helped to track a lot of the missions that were going by both the Americans and the Soviets. And one such mission that we did track has a very funny story behind it. That is the Luna 9, and this image here is taken from a camera that was aboard Luna 9. Now, if you're unfamiliar with Luna 9, it's a Soviet mission. It was 1966 when it got to the moon, and it didn't have cosmonauts aboard, so no people on it, but it did have a camera. And the goal of the whole Luna 9 mission was to soft land on the moon, which is just jargon for crash, but technically a crash humans can survive, so we're gearing towards human spaceflight. Now, unbeknownst to the people in the control room at the time, though, it did also have a camera. So they were tracking it get to the moon. They got the radar, they got the radio signal back, the telemetry from Luna 9. It's landed, all is well. They thought, job done. But then the signal started to change, and it came in the form of a radio fax signal. Now, radio faxes were very commonly used at the time to actually send pictures. So a lot of newspapers would have a fax machine because that would be how they send pictures back and forth. Unfortunately, for the radio telescope control room, there was no radio fax machine. So they had to ask a local newspaper to borrow theirs, and then once they got their hands on it, they were able to descramble that image. And this is actually a very historic photo. It is the world's first ever picture that was taken on the moon. So it is very historically important. And it is also the Soviets' property because it's their mission. So they waited overnight, waiting for the Soviets to release their own image to the world. That never happened. So the British tabloids, who we use their fax machine, they said, well, we'll help them out and we'll publish it for them. So it ends up in the British tabloids and newspapers in the morning before the Soviets had released it to the world, and it's technically their image. Now, you would expect Moscow to be very angry at Jodrell Bank over this, but the only sort of comment that they made when eventually they got into contact at Jodrell was, you've got the aspect ratio wrong. And then they carried on operations as normal. So there was probably a little bit of anger there, but overall it wasn't really worth it, and worth not having somebody to track the mission, I suspect. But anyway, we accidentally hacked the Russians with the Hubble telescope as well. So there you go. Now, that does bring us to today as well. Now, you may have heard of the word pulsar, because it's everywhere around site. And that's one of the main areas of research that we still do today here at Doddle Bay. Now, pulsars are often found in these areas of the galaxy. And these are nebula. They're really awesome areas if you want to study star formation, because it's inside here that stars are being formed. A nebula is essentially a big cloud of hydrogen gas. There's probably other gases in there as well, but you need hydrogen to make a star. So hydrogen gas. It's got dust in there as well. There'll be other trace elements too. But it's the essential ingredient you need to make a star in a lot of it. And that's why you get a lot of stars being formed in these areas. Now, unfortunately, if you've got an optical telescope, it is essentially a cloud for an optical telescope. Meaning if there's something really deep in the nebula and these stars are behind loads of gas and dust, you're not going to see it with an optical telescope because of the gas and dust of the nebula at the front. So visual telescopes are not great to study star formation when they're in a nebula. Whereas radio waves and infrared light, they can all get through a nebula. So our telescopes can potentially see what an optical telescope might not be able to see. Now, for us, we're actually studying the end bit of star formation. We're actually studying star death because a pulsar, pulsar is actually a dead star. So this is actually the end of a star's life. For a big star, when it goes supernova, I mentioned one of those before, it's really powerful. So the outer layers of that star explode into space, and they cool down over time and turn back into a nebula. So that's why you find pulsars in nebula as well. It's a cycle. It's a cyclical thing. Star birth and star death. Now, a pulsar is what's left over when a really big star dies. It's all the bits that didn't explode away. And essentially what happens is when the outer layers have gone off into space, what's left over has nothing to keep it up outwards. So gravity will take over. And what will happen is what's left over will collapse. And that is your neutron star, which is basically just a version of a pulsar. But a pulsar is a neutron star. It just does one extra thing. A pulsar, you get your neutron star. It spins really, really fast. But because it's spinning really fast and you've got lots of physics going on, it basically shoots out radio beams of light from its magnetic poles. And that is what a pulsar is. It's a dead core of a star spinning fast, giving out radio light. But because it spins, from our viewpoint on Earth, it's going to be like, you know, when you see a lighthouse on the horizon, it looks like a flash because of that spin. And that's why it's called a pulsar. It's a pulsating star. So they're really, really fun objects to try and find. And they're also really, really useful to study as well. Now, pulsars, their spin, it doesn't slow down or speed up for no apparent reason. There's got to be some sort of mechanism, some sort of physical object that you input into the area that makes it slow down or speed up. Sometimes, when observing a pulsar, they observe it slowing down or speeding up. Minutely, not a lot, but minutely, enough for us to go, something is going on here. That's quite interesting. And sometimes that is actually a gravitational wave passing through the pulsar, given off by a black hole that's somewhere nearby. So you can actually use them to study black holes. And that's really useful because you can't see a black hole, but you can just see a pulsar. So that's really useful. They're also really compact and they've got a lot of mass. So they're not very big, these pulsars. They're often about the size of a city. But they can weigh anywhere between the mass of the sun up to maybe 3 times the mass of the sun if it's a bigger one. And therefore, they've got a very strong gravitational influence on the things around it as well. So you can use pulsars to test Einstein's theories as well. Now, we don't have that capability to do that here on Earth because we don't have these types of conditions here on Earth. So these are basically perfect labs in space to test our current theories as well. So they're really useful. And that's why we spend a lot of time studying pulsars. Now, I did mention before a black hole. And I did say it is a little bit harder to spot those. We do actually have radio images of black holes. However, these are not our pictures of black holes, because to get this picture, it required multiple radio telescopes from across the world. Over a couple of years, they looked at the same object, this being M87, a galaxy with a supermassive black hole at the center of it. And then all of that data over all of those years had to be combined together. So essentially, we're using a radio telescope that's now the size of the Earth, a big radio telescope, and that is how we're able to get a direct image of a black hole. So it takes a lot more resoluting power to get a direct image of a black hole. And so the more resolution you want, the more light you need to collect. Therefore, the more telescopes you need to basically use as one big telescope. And so this was done with the Event Horizon telescope. It was a network of telescopes around the world. And they were able to actually get a direct image of a supermassive black hole. Now, you would think that because we've known about supermassive black holes for so long, that this image has got to be fairly old, right? This was only compiled in 2019. It's not even 10 years old yet. So it's only very recently that we've been able to do this, because we've built more radio telescopes and we can connect them now. Of course, we have to do it for your own galaxy as well. So we did it for Sagittarius A star. This is our galaxy's supermassive black hole at the center of it. As you can see in the picture, we've got basically a big glowing disk around a black ball. And that black ball in the middle is the actual supermassive black hole. It does not matter what type of telescope you have, how big a telescope you have, you will never be able to see a black hole in a telescope. And it's because of the black hole itself. Now, black holes, if you didn't know, they're very, 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 very powerful objects. So imagine I have a black hole in this canister here. Essentially, what a black hole does, its gravity is so strong. So if you get too close to this black hole, and in this picture, the start of the black circle is that boundary, we call it the event horizon. You cross that boundary, the gravity of the black hole is so strong, it does not matter what you are, you'll get pulled into the black hole. So, I've just removed the secret there. So all of the light, all of that matter gets pulled in, and that means it can't reach our eyes, it can't reach our telescopes, because it's being pulled towards the black hole. And that is why it doesn't matter how much you try, you will never see a black hole, because all telescopes rely on picking up light, and it's simply put that black holes just pull that light towards them. So we never see that light. So, but we can see all the stuff around the black hole instead. So we can see its accretion disk, all the gas swirling around it. That is far enough to be influenced, but not far enough that it gets pulled in. And that's what these pictures are actually showing you. So a direct image is sort of a half-truth. It's a direct image of what we can see of a supermassive black hole. So that's what they look like. And this is, as I say, it's not a simulation. This is a real radio image, which is awesome. Now, it's important to understand that radio astronomy is one bit of a whole of astronomy. Now, these days, we do tend to do what we call multi-wavelength astronomy. So that is all types of telescopes will look at the object, and then you'll use all of the data from all of the telescopes to get a better understanding. So again, you need to go back to the story I told you at the start about a Tycho Brahe star. We rediscovered it in the radio because it was no longer visible in the visual. But then, now that you know it's there, you can get more powerful telescopes and you can look and you figure out the physics. And then also pulsars, we won't be able to see them with an optical telescope, but we can see them with a visual telescope. And so that is why it is important that we do have multiple telescopes, not just optical telescopes, like the Hubble Space Telescope. Granted, it is actually my favourite telescope, but I shouldn't have a favourite. I work at double rank, but I do. It's the Hubble one. And this is an optical telescope, so this is taking pictures of the same type of light our eyes can see. And one of my favourite pictures it ever took was the Hubble Deep Field. And this, again, demonstrates how big the universe is. And so every point of light in this picture, believe it or not, is a galaxy. It's just really far away, so it only looks like a pixel on the image. But it is a galaxy star, so it contains billions of them. It's just really far away. Now, you would expect with there being a lot of dots in this picture, again, this has got to be a big area of the sky, right? No, it's actually not. And that's what makes this even scarier and also kind of wonderful. If you took your thumbnail and you put it up to the sky, the kind of area of your thumbnail is about the field view of this picture. So it's not that big at all. So whether that gives you an existential crisis or not, welcome to astronomy. But yes, so if you get images of optical and radio and combine them, you can actually get a better understanding of what's out there. Because certain things might be visible in the optical, but not the radio, and vice versa. They might be visible in the radio, but not the optical. That, unfortunately, does bring me to the end of my telescope talk. So thank you so much for listening. If you do have any questions at all, I'm more than happy to answer any you have. If not, I do hope that you enjoy the rest of your visit here, and thank you very much.